So for number 5, it was converting into rectangular form. We're dealing with polar form, and so that's the idea. You have r's and thetas. You want to get rid of the r's and thetas. We want to bring back x's and y's. All right, so that's what we're going to do. First off, we have the sine of theta. Sine of theta is equivalent to y over r. So I could say r minus r times y over r is equal to 0. All right. The tendency might be to do something like replace the r with a square root of x squared plus y squared, but that's going to make things unnecessarily complicated. The idea would be to try to get everything in terms of r first. So basically, if you're looking for an algorithm, that it would be get rid of any evidence of theta first, and then start worrying about the r's. Life ends up being a lot easier that way. All right, so if that's the case, I have a nice little cancellation right here off the bat. So we have r minus y equals 0. All right, I could also write that as r equals y. All right, so r equals y. And then do my substitution for r. All right, making that the square root of x squared. Doesn't matter what device I use. I can't correct for brain farts. Am I allowed to say that? I don't know. Doesn't matter. I say a lot of things I probably shouldn't say. All right, so we have square root of x squared plus y squared equals y. Actually, in the grand scheme of things, that's probably not the worst thing ever. So it's a question of, what are the requirements of the problem? If the requirements are something simple like just get it into rectangular form, mission accomplished, right? If the requirements are to get it into some kind of standard form, then we want to go a little bit further. And by the way, there's other pathways you can take. I mean, if you wanted to, you could add the r sine theta to both sides immediately, and r sine theta is the definition of y, so you can make that substitution right off the bat, right? But if I square both sides, for example, you get x squared plus y squared equals y squared. Cancellation. X squared equals 0. Making x equal to 0. So after all that, you have that one little relationship there, and that's it. All right. The rectangular form, it all depends on what you're looking for. Yeah. So once you get it in x's and y's and not r's and thetas, you're done with the problem. You could have GCF'd out an r if you wanted to. Make it r times 1 minus sine theta. Move some things around. There's all different possible pathways. All right. So, how would you check something like this? Well, not easily, I don't think, because you still have to do something to it in order to check it on your calculator. Right? You'd have to solve for r first, and then put that result in your calculator. Now, if you kind of play that out, say, all right, I'm going to factor out an r, and you'll have a 1 minus sine theta. Then what do? Divide it out. So you can get some kind of semblance of the final answer that way. But this is telling us something more. It's not really saying it's a single point. It's really saying that it's a vertical line. All right? That is not my pen tool, so that's not going to work. So having a sense of what your final objective is also important. All right. Numbers 6 and 7, both going into polar form. So it's really just a matter of getting rid of your x's and y's and introducing r's and thetas. But more so, it's a matter of just getting rid of your x's and y's. Introducing r's and thetas, it's not as important, because sometimes you'll only be able to introduce an r or only be able to introduce a theta. You may not be able to introduce them both. Right? If that's the case, then don't force the issue. If you can only get a theta in there, all right, that's fine, as long as there are no x's and y's.
Is that the same thing for rectangular form? You can only get an x or you can only get a y?
Exactly. Yeah, you don't have to have them both. All right, so for this one, I would be thinking about maybe distributing, because I have an x minus 4 squared. Now, I could be thinking like x equals r cosine theta. That would be fine. I can make that substitution, but I'm not interested in distributing out r cosine theta minus 4 as a binomial squared. That doesn't seem like fun. I'd rather distribute it out in rectangular form and then do my substitutions. And then you never know. Maybe something nice will happen. I mean, something nice is going to happen. That's why I chose this problem. But you never know. All right, so distribute it out. Oh, look, 16s cancel. That's awesome. All right. We could also reorganize into the first galactic empire. Movie reference? That was an easy one.
That's Facebook?
No. Oh. It's a good attempt, right? Right genre, I guess. Well, actually, it's the spoof of the right genre. I'm losing the ability to draw squiggly brackets, so for whatever reason, I'm taking an unnecessary amount of time making a squiggly bracket. And so, yeah, Spaceballs was a spoof on Star Wars. That was a direct quote from Emperor Palpatine in his speech in Episode 3, Revenge of the Sith, which is not historically considered to be one of the best Star Wars movies. However, there are some quotable moments like that one. Oh, yeah. Yeah, hands down. I mean, there was a big payoff at the end. I'll start with that. Like, lightsabers that were really lightsabers. Instead of, like, force projections, which is apparently now a thing. That's good to know. Moving forward. They say that the new movie is going to make you rethink not only the original trilogy, but also the prequels, which is scary because I liked what I thought about the original trilogy. But if what it's going to make me rethink is that they were all just force projections and they didn't really exist at all, and that they're all just figments of someone's imagination, that's going to be a problem for me because I've based my entire life around Star Wars, for better or for worse. So x squared plus y squared is r squared. So we have r squared minus 8x equals 0. All right. Now, I can make those recognitions because of years of experience. I'm fluent in this stuff. You know, sometimes to a fault because you might have seen it, like in the last problem. The r sine theta, you might have, I think it was r sine theta, whatever it was. What was it? Yeah, r sine theta. If you're reflecting back upon rules, you might have said, oh, that's equal to y. I'll just make that substitution. And then I did something different, and you're like, ah, well, there goes that idea. You were right, I was right, everybody's right. You know, so that's the idea here, is that your knowledge of the rules will take you in a direction. If it takes you in a different direction than mine, that's fine, as long as it's based on an appropriate rule. All right? So here, I noticed that I had an x squared and a positive y squared. And because I know that x squared plus y squared equals r squared, I can make that substitution. So things like reference sheets and note cards on tests and things like that, and we'll talk more about that when we get closer to a test, but they have their place, they're useful, they're good like backup plans, but I found historically that the people who struggle are the ones that over-rely on that sort of thing, meaning they just wrote down every formula that they could find in their packets, and they're like, okay, I'll just use that for the test and everything will be fine. If you don't know enough to know when to look at your note card, then what's the use of it? I mean, it's kind of like I equate it to trying to translate a sentence or interpret a sentence by decoding or defining every single word in that sentence. So somebody says the boy will ride the bus, and you're like, okay, what does the word "the" mean? All right, let me get the dictionary out. All right, good. Boy, all right, okay, opposite of girl. Will, all right, future tense, all right, this sounds good. Ride, okay. The oh wait, I know that one. Wait a minute, do I? Okay, well, I'll look it up again just to be safe. The bus, okay. All right, cool. I think I got it. Boy will ride the bus. And then, so that's great. So something that you should have understood in like a second took you like 3 minutes to understand. You know, it's like learning a foreign language. All right, so learn the rules and become fluent in the rules so that you don't have to constantly go to a resource for it. All right, that's why I keep harping on this unit circle stuff, because there is a reason for it. So r squared minus 8 times, instead of the x, I could say r times the cosine of theta. I can say that because I know that as a fact. All right. Now at this point, like, all right, done, I guess, depending on the instructions. But if it's one of those things where you're like, okay, I recognize what this is. This is a circle with a center at 4, 0, and a radius of 4. I could plot that on a graph if I wanted to. I want to make sure that what I just came up with in polar form is equivalent. Then you would want to solve this for r. Right? So you could pop it in your calculator, make sure it gives you the right graph. All right? So if that's the case, then I would move the 8r cosine theta to the other side. So r squared equals 8r cosine of theta. And then I would divide out the r. So 8 cosine theta. Now, that little move right there that I just did, dividing both sides by a variable, in function form, rectangular form, that's like a cardinal sin. But in polar form, it's perfectly fine. Because in rectangular form, if you had a solution where x equals 0, that's a location. It's an x-intercept at 0. All right? In polar form, if you have a solution r equals 0, it's a trivial solution because it's saying that you have, technically it's a solution. So anything that's technically a solution, but not an overly meaningful one, we call that a trivial solution. All right? In those cases, you tend to dismiss them because it's like, okay, I got an r equals 0 as a solution, but what does it mean? It's a circle with a radius of 0. So a geometric figure with no radius would be nothing at all, right? So it's no figure. There's nothing there. So if that's the case, then why would we even consider it? So in the rectangular plane, x equals 0 is a location. In the polar coordinate system, it's a radius. If a radius is 0, then there's nothing there to begin with, so we can dismiss it. All right, so you don't need to give me r equals 0 and r equals cosine of theta, which is good because half the students forget to do that anyway. All right. Now we have this one where, well, if that were a plus sign, I would start thinking about maybe x squared plus y squared equals r squared, but it doesn't look so good. I can clear out the 4, try to make it not a fractional equation. So x squared minus 4y squared would be equal to 4. Now, what I gave here was a standard form of a hyperbola. All right, center 0, 0, and then they have different distances from center. But this is also a hyperbolic equation. But again, we want to get it in polar form. All right, so we're going to make some substitutions. So r cosine theta squared, because the x is squared, and r cosine theta is the same as x, minus 4 times the y squared. Y is r times the sine of theta as a quantity squared. All right. For some of these cases, you want to be on the lookout for some trig identities, because sometimes they can come into play. You never know. In this case, if we clean it up, we'll get r squared cosine squared theta minus 4 r squared sine squared theta equals 4. Now that's a polar equation, so we're in good shape. If we want to solve it for r, it's not going to take much doing, so that's even better. All right. If this had a plus sign in it, I mean, that 4 is kind of mucking everything up, but if there were a plus sign here, then I would start thinking about some trig identities to maybe clean it up even further. But not the case here, but definitely something to be on the lookout for. Is that a hint? Yeah, of course it is. It always is. Oops, there it is. All right. The good thing about this this approach is that, well, a couple of good things using the iPad is that it has a more sensitive microphone, so you'll pick up all the mutterings to myself when you listen to the YouTube video. It's somewhat entertaining, but also more importantly, I can edit the video when I screw something up to kind of cover my tracks, as opposed to the other form where I had to kind of leave it alone. And so it should make for a cleaner experience. Anyway, r squared would be equal to 4 over cosine squared minus 4 sine squared. Now, again, if you want a calculator friendly, take the root of both sides. Now, you can never go wrong throwing a plus or minus in front of it. Tends to be overkill because the sign tends to, oh, there it is, get in there, tends to refer to the direction of your movement around the figure. Most of the time, and there are exceptions to this, but most of the time, a positive would be a counterclockwise movement with a negative being a clockwise movement. But generally, the positive or negative variation of this ratio would give the same figure. The positive or negative sign would dictate your movement around the figure. Sometimes important, sometimes not.
How did you identify the hyperbola?
Oh, the hyperbola general or standard form is x minus h squared over a squared minus y over k, or y minus k squared over b squared equals 1. All right, that's one form of it, the relevant form. Another variation would be the x fraction and the y fraction swapped with the minus sign still in between. The ellipse standard form is the same as this, just with a plus sign. All right. And you can see that they're both variations of a circle equation. Because basically, throw in a plus sign here and ignore these two bad boys, and you have a circle equation. All right, that's generally how it works. So it'd be a radius of 1, but still. All right, that's the general idea. So definitely worth some time to review conic sections, just the different types of things. Not so much now, because you could sort of get away with it. I mean, I refer to it as a hyperbola. It's nice to know that. But in reality, the skill is just getting us to a point where we have a model that we could pop into our calculator. Coming up with this graph, you could still do it in the calculator. That's what I mean by it's not the end of the world if you don't know it now, because you could still come up with this graph. You just have to solve this equation for y. All right, so not the most entertaining thing to do in the world, but it's doable. All right, but when we get to the 3D stuff, we'll need to kind of bone up on the conic section material. All right, so 4 minus the 4 sine of theta. This goes along with the example we did last class, in that there are convenient values along the unit circle for sine ratio, cosine ratio, tangent ratio, and if you know what those convenient angles are, then you're going to be in good shape. Right? So anything along the axes is going to work for any kind of function. I mean, sometimes you'll get undefined, but that's an answer in and of itself. All right? But the reference angles that we're interested in for the sine function, we want reference angle of pi over 6. Or 30 degrees, if you like degrees. Because you may remember I said, you agreed happily, that we can go back and forth between radians and degrees for this topic because our graph has both radians and degrees on it, so you can work with them interchangeably. All right? So, including the 0, 90, 180, 270, 360, I also want to have any angle that has a 38-degree reference angle. I like the radians because, for me personally, it takes, anytime I could take a mental break, I find relief in that because I feel like I'm always thinking. So, reference angle of pi over 6 would correspond with any angle that has a denominator of 6. So I already know just by looking at my graph grid what angles I'm shooting for. All right, so when I'm making my table, I'm going to start with 0. So again, theta is our independent, and then r would be our dependent. I'm going to start with 0, then I'm going to go to pi over 6. Then I'm going to hop up to pi over 2, then go to 5 pi over 6, then go to pi, then 7 pi over 6, then 3 pi over 2, then 11 pi over 6, and then the last one would be 2 pi. Then I could just plug and chug. And you could let the calculator do the chugging for you if you want. You know, it can be tedious, but if you know some unit circle stuff, it's going to be a little bit easier. All right, so let me just make this a little bit more visible. I got to kind of find the perfect balance between what I can see here and what I can see there. So 0. Sine of 0 is equal to 0, so this part is going to 0 out. All right, so 0, 0 is going to be a point. The good news is any point on the x-axis has a sine value of 0. The reason why is in your unit circle, the sine of theta is the y value of any coordinate. If you're on the x-axis, the y value has to be 0. So
Wait, that's 4. That's
4, 0. Well, that part was,
Yeah, the 4 sine theta is 0.
yes. All right, and so for pi, we're also going to get a 4, and for 2 pi, we're also going to get a 4. All right, only because the sine of theta part is going to 0 out. Now, pi over 6 gives us a sine value of 1/2. 4 minus 4 times a half, so 4 minus 2 is 2. Sine of pi over 2 is 1, so 4 minus 4 is 0. 5 pi over 6 is still a positive value for sine, so it's going to give you the same value that you got for pi over 6, which is going to be a 2. And we get to the 7 pi, oh, and by the way, the 3 pi over 2 would follow the same idea as pi over 2, except it's going to be negative, so we'll get to that in a second, but you could still rely on the 1 versus negative 1 relationship. All right, negative 1/2 is what you get when you pop in a 7 pi over 6. So that's going to make it a 4 plus 2 is going to give us a 6, which is going to make this one a 6. If I pop in a 3 pi over 2, that's going to give me a negative 1, so 4 plus 4 is 8. All right, so now it's just a matter of plotting these. Now, you could also set up your calculator to give you these convenient values. You know, it takes a little doing. It involves a table set. It's sometimes more trouble than it's worth, so I'm not going to bother with it right now. But it is something worth looking into at some point. All right, but for now, I'm going to plot 4, 0. So 4 in the direction of 0. Two in the direction of pi over 6. 0 in the direction of pi over 2. Okay, so that's the pole. Then 2 in the direction of 5 pi over 6. Then 4 in the direction of pi. 6 in the direction of 7 pi over 6. We have to estimate that 6. 8 in the direction of 3 pi over 2. Like here-ish. 6 in the direction of 11 pi over 6. Let me just scoot it over. For me, anyway. And so we have pretty much what we need. In terms of drawing ability, gets the job done, but that would be, if you follow the models,
Cardioid.
a cardioid.
No,
Well,
It's a -4, so that makes it different.
well, it's going to be a limacone in that. Let me just. I'm scrolling on my screen as if it's going to be helpful. It's going to be a limacone because your coefficients are not exactly the same, but it does look like a cardioid. So it's a good opportunity to talk about the differences between the two. A limacone could have the loop or not have the loop, right? And it could be oriented vertically, horizontally. The cardioid is oriented one of two ways, right? It's either oriented this way or vertically if you have a sine function, right? So it has a particular look. Right, so it can be weird to distinguish between the two, but this one would technically be a limacone, but it does look like a cardioid. All right. In the end, what I think I mentioned last class is that I'm not asking you to name them. So if you look at that and say, "Oh, it looks like a heart," like cardiac. Oh yeah, that works. It's probably a cardioid. In the end, yeah, that works. So. A lemniscate.
Oh, I know what it says, but it's taking the square root of that, and that's the square root of -1, and that's undefined.
Right, but as we know, all right, the remaining problems here are all related to other types of figures. The first one is a little bit more interesting, I think, because you're going to get a shape that's probably unexpected. Then 11 and 12, they're kind of consistent with each other. So let's take a look. Being able to draw, or at least have a sense of the drawing of these, is kind of important, because if you don't know what the figure is supposed to look like, then in terms of finding the area, it could be problematic. Right? So 6 times the sine of 2 theta. We're looking for convenient values for the sine function around the unit circle. The issue that comes up here is that convenience is sort of in the eye of the beholder. In this case, let me go with a highlighter. It's that 2 theta that's good. Oh, that's not very highlighted. Better, I guess. At least something showed up. What's going to happen here is the convenient values for sine are not going to be as simple as just saying, okay, well, where are my y values around the unit circle?
I was wondering because I put the table set like you said, and I just did pi over 6 for the table set, and I would just like guesstimate where the 1.00 something would be in around the graph. Like, would that be?
Yeah, but even better would be make your change of table pi over 12, so that every step around would, or every step down your table would correspond with each step around.
Okay.
I think that
But
would
you'd
be
be fine even if it was like just a guesstimate because you put the table values on the calculator. It's like whatever that is,
right
over something.
Exactly. Yeah, but if you make it line up with pi over 12, then at least you'll have a better sense of what the benchmarks would be.
I don't know if what I did was the best way, but I took the same reference angles as the previous one and just divided it by 2.
That's the idea. Yeah, that's what I was getting to. So if we know that pi over 6 is what we want for an ordinary sine function, we have to understand that this is double that. So if I were to plug in a pi over 6, then that would make it pi over 3. It would make it 2 pi over 6. And therefore, it would make it not a convenient reference angle. So what we would be looking for is a relationship that allowed whatever the argument is, in this case 2 theta, to be equal to the convenient reference angle of pi over 6. All right. So then, if that's the case, if I were to replace the entire 2 theta with a pi over 6, then I would be taking the sine of a convenient value. All right. So then I would solve this for theta. and I would get pi over 12. So that would be my convenient reference angle. So I would have my 0, because you really can't go wrong with 0. I mean, I'm sure I'll find a way. But I want theta and r is what I wanted. So start off with a 0. We go pi over 12. And you say pi over 12. Yeah, but if you look at your graph, it has over 12. I mean, if I gave you something like the sine of 7 pi, you might not be happy with me. But this is fine. We can work with this. So the next one, if we're going around, you might say pi over 2. All right. If that's the case, though, you got to understand that pi over 2 is going to become pi. All right. So am I going to skip something that's important? Maybe. If I put in a pi over 4, let me just jot that down. When I put it in here and multiply it by the 2, it's going to make it a pi over 2, which is convenient. All right, then I would get to the pi over 2. Then a 3 pi over 4. Then the 11 pi over 12. All right, so all we're doing here is looking for convenience. 13 pi over 12. Oh, I'm sorry, the pi. I want to forget the nice ones. So then continuing to work your way around. And it's all right. You might miss a couple along the way. And if that happens, you'll either realize that you missed a couple and go back and try to figure out some more points to include. Or you'll say, oh, I have enough points to have a sense of what this figure is supposed to be. Because again, the names of it, not as important. The actual shape is really what we care about. All right?
So the points that we pick for theta is just points that we choose, like just randomly?
Choose as you work your way around the unit circle in such a way that it gives you nice, convenient sine ratios.
Okay.
All right. So next up would be 5 pi over 4. I can continue. But let's actually see where these go. You know, maybe we'll have enough to get a sense of what's going on just by these calculations. So if I plug in a 0, I'm looking at the sine of 0, which is 0. So the whole thing's going to 0 out. If I plug in a pi over 12, that's going to become pi over 6. Sine of pi over 6 is 1/2, so 3. Plug in a pi over 4, that becomes pi over 2. Sine of pi over 2 is 1 times 6 is 6. Sine of pi is 0. 3 pi over 2 is what this will become when you multiply it by 2. So negative 6. 11 pi over 2 becomes 11 pi over 6, which is negative 1/2, so negative 3. Pi becomes 2 pi, which is on the x-axis, so 0. 13 pi over 12 would become 13 pi over 6. And you're like, what's that? Well, it's more than one turn around the unit circle, but it would put you in the first quadrant. Right? 13 pi over 6 would be right after 12 pi over 6. It would be the first pi over 6 after 2 pi. So equivalent to pi over 6 gives us 1/2 multiplied by 6 is 3. All right. Let's see if this is going to work in terms of the line. Undo. Undo again. I'll just leave it lineless. All right, so now I want to plot. All right, so 0, 0 is nice. 0 units in the direction of angle 0. 3 units in the direction of pi over 12. Six units in the direction of pi over 4. 0 in the direction of pi over 2, so that's nothing. It's still at the pole. Negative 6 in the direction of 3 pi over 4. All right, so negative 6 in the direction, that's a weird thing to say because it's not really in the direction. If I'm standing at the pole looking at 3 pi over 4, negative 6 is telling me to take 6 steps in the opposite direction. All right, so it's going to... to 7 pi over 4, exactly. All right. 11 pi over 12, 3 steps away from that. That's going to bring us 3 steps in the direction of 23 pi over 12. It was 3, right? Yeah. 0 steps in the direction of pi, not helpful. 13 pi over 12, we're looking at 3 steps in that direction. So that puts me right, yeah. All right, so you do a bunch of calculations, you stop, take stock of the situation, and then make a determination, well, have I gone far enough? And the answer is yes, if you have enough information to determine that you've made like a revelation or had a revelation. Well, this is clearly the big difference. No. I mean, if that's the case, then good for you. If you recognize the function, you might know what this is supposed to look like to begin with. It's supposed to look like a 4-petal rose.
Yeah.
It looks like I have the makings of maybe a petal over here and maybe one down here, but not quite enough. Right? So maybe we grab a few more points till we see what's going on.
5 pi over 12.
5 pi over 12. Right, so actually we can get 5 pi over 4 in there before. So we can get 5 pi over 4. We could also get 3 pi over 2 because that would be clean. Then the next one would be 7 pi over 4. Just slip it in there. Right. Then 23 pi over 12, was that the last one? Yeah, 23 pi over 12, and then 2 pi. All right, so the 5 pi over 4 would become 5 pi over 2. So this is where it might get interesting, but if you know how to count around the unit circle, this doesn't require a calculator. It doesn't require any more knowledge than just knowing your unit circle. So 5 pi over 2, again, is what this would become. So 1 pi over 2, 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. 5 pi over 2 goes to the same place as pi over 2. So whatever I get, it's going to be 1. So whatever I would get for pi over 2 would give me the correct result, or at least in that location. So,
Professor, I'm sorry, I need to say 5 pi over 12. Well,
5 pi over 12.
As our angle of 5 pi over 12, it would be, R would be 3.
Oh, I missed those. Yeah, we'll get 5 pi over 12 and 7 pi over 12 also. Yeah, okay, good. I can chuck those in there also. Yeah, why not? Make a new column. Well, I've learned that drawing lines is not my strength. So 5 pi over 12. We'll throw in a 7 pi over 12. Still within one turn around the unit circle, so that would work. All right, so if I plug in a 5 pi over 12, I get 5 pi over 6. So that's the sine of 5 pi over 6, which is 1/2, so 3. So 3 steps in the direction of 5 pi over 12. Where are you? 1, 2, 3. And then 7 pi over 12 is 7 pi over 6 when you plug it in. So negative 1/2, so negative 3. So find 7 pi over 12 and take 3 steps in the opposite direction. Okay, so actually that's going to be really helpful, because now I have a closed loop here and a closed loop here. All right. Now, whether you're using your calculator or just general knowledge of these polar graphs, you can come up with the rest of it just by what you know here. All right, so if you were to plot in polar form 6 sine of 2 theta, you'd have a 4-petaled rose. All right, it wouldn't look like a rose. That's not really, I don't know why they call it that. But then again, they're also using terms like lemniscates, limesons, and cardioids. So clearly we're in the realm where we're just making up names for stuff. But if I know that I have to reproduce this on the other side of what would be the y-axis if it's in rectangular form, then I can start assuming some coordinates, like this one here and this one here. If it's going to be symmetric, I should have corresponding points at 3 pi over 4 and 5 pi over 4 to go along with pi over 4 and 7 pi over 4. All right. Also, we have this guy here, the one going to 13 pi over 12. There would also be one going to 17 pi over 12, just because it seems we're taking 3 steps in the direction to the over 12s in all the other quadrants, so why not here also? So if we can make those assumptions, then we have everything we need. And that would be your 4-petaled rose. Right? And it looks glorious. Topic. Because, yeah, this is some kind of polar graph. R equals f of theta, so a function of theta. It doesn't look like any of those classical curves that we talked about, because I wanted a generic looking graph. Right? So theta is going from alpha to beta. That's just, they do that to represent bounds within a polar graph. So in rectangular coordinates, if you were integrating on the interval of 1 to 2, it would be your A value and your B value. Here they tend to say alpha and beta, but that's really just textbook jargon. I get away from that almost immediately and go back to A and B. As long as you know that these aren't the same A's and B's as they would be in the rectangular coordinate system, it's perfectly fine. All right? I don't think anybody's losing sleep over that. So what we're looking at here in terms of a formula, this bad boy, 1/2 r squared d theta. All right, this is a variation of 1/2 r squared theta, which should sound really familiar if it was a topic taught in your pre-calc class. Also commonly skipped topic. So let's just go back for a sec and talk about the area of a sector and an area of a segment. Area, well, we'll just focus on a sector right now, of a circular sector. That area would be 1/2 r squared times theta. All right, so what that would be is if you were given some sort of circular region, I'll just go with an ordinary circle, and you needed a slice of the pie, it would give you this area. Emphasis on the term area, because we have a formula to help us find an area that could only be helpful. Right? Just like when we were learning about volumes of revolution and areas under the curve in Calc 2, it was still based on some knowledge of area, some prior knowledge of area based in geometry. So the disk method, what was its main emphasis or the root of that method? Area of a circle, right? So, and when you get into cylindrical shells, it was still a circular relationship, but just expanded out to make it a cylinder. Right? No different here. It's just we're using a different area of some sort of circular region formula. So, depending on what your theta is, it could give you a tiny sliver of the pie, or it can give you the whole thing. So, if you pop in a 2 pi for theta here and simplify it, right, that would be one full turn around the circle. What do you get?
1.
Well, what should you get if I wanted the area of one full turn around a circle? Pi should be part of it. Pi r squared, as in the area of a circle, right? So it's kind of a question of what begets what, like what came first. In this case, you're looking at the origin behind the area of a circle formula, right? So if you know this, you can find the area of any part of a circle. If you want the whole thing, you pop in a 2 pi and it simplifies down to pi r squared, which is why we have that formula, pi r squared is the area of a circle. It doesn't come without this piece of information, right? But not the kind of thing that you're probably ever introduced to or ever studied. Like, it's just a formula. You know, C equals pi d. It's just another formula, right? But this is, well, here's an example of another formula, but this is a better one because this one gives you more than the area of a circle formula could ever give you, right? So then how does that benefit us? Well, if you're looking at this diagram on a micro level, aka let's zoom the hell in on it. I had a little eyelash on the screen there for those keeping score at home. I'm gonna thicken this marker up as soon as I remember how to thicken it up. There we go. So this would be our starting point, right? Right, yeah. And let's say I wanted to go just a teensy tiny smidge to the right. Now, I think we'll all agree, just based off the picture, that there's no way I could just make this part of a circle. Like, this is not some subsection of the circumference of a circle. Maybe a part of it is, maybe you could look at this piece and say, oh, that's the edge of a circle. If I just drew, let's say this guy right here. Let's say I just drew, oh man, it would help if I could draw. You could say something like that. Like maybe I have a circle where this section of the circumference of the circle corresponds with that curve. That could be the case. But then what do we know about that circle? Do we know any details about it? Do we know its center? Do we know any radii measures? No, absolutely nothing. All right, but what I do know is that this is the origin and that this is some point in space from the origin that we can call R. All right, then if I were to take an ever so tiny step in the counterclockwise direction along the circumference, just a teensy tiny smidge, like the teensiest tiniest, so like right out to here, that little teensy tiny segment right there, which just seems like a rectangle because again I can't draw, that would be a sector of a circle, some circle. I don't know what the circle would be. I mean, it'd be a big one. You know, you could extend it out. I can go dot 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 in that direction, dot 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 in that direction, do some better dots over here and erase the crappy ones. But I can draw a circle going all the way around, but maybe it's only that teensy tiny little sliver that I care about that corresponds to that curve. All right? So if that's the case, then I would be looking for this infinitesimal change in theta. Instead of a huge change in theta, I only want this teensy tiny little sliver of change in theta that we'll call d theta. All right, so if I'm telling you that all you have to do is find every single teensy tiny sliver of circumference as you work your way from the start point to the end point, and then add them all up, that makes it seem a whole lot easier. Because what we're doing is we're taking this formula, 1/2 r squared theta. Now, I don't want a whole theta, I just want a smidge of a theta. So let's make that a d theta. All right, now I want to collect all those little slivers. How do we do that? We integrate them. That's where our formula comes from. All right. So, what do we learn from this formula? if I know where the region starts and I know where it ends, I'm pretty good to go. I mean, I should know what the bound of the region is defined by, right? If it's not given, I have to figure it out based on some context or something along those lines. But doable, all right? The extension would be that if I wanted to find the area between any polar graphs, I would just find the difference between their radii squared, right? So it's a 1/2 r squared, sorry, a 1/2 r squared d theta for the outer figure, and then a 1/2 r squared d theta for an inner figure, subtract the two. This is the simplified form of that. All right. The arc length is a different story. I think it's a different story for a different time. Because there's really, I mean, there's a good origin story to it in polar form, but really all we need to know is that if we take the rectangular arc length formula that we learned about last week and just do some substitutions to that, we'll get this formula. All right, so basically, because you see a dr d theta here, it's going to be reliant on our ability to take a derivative involving a polar function, which we have not learned yet. All right, so there's more on that later, but there will be an exciting conclusion to the arc length. But we can certainly use it once we learn how to take a derivative. But I do want to show you where it came from, because that's kind of my thing. All right, so sketch figures, find the arc length and the area of each of the following. It's all formula based. And you know what I can do? So r equals 3. Now, in theory, you should not need any calculus-based formula to figure this one out, because r equals 3 is a circle with a radius of 3. If you know that piece of information, you're pretty good to go. But let's use our newfangled technique here. Let's see if that's gonna be a rewarding approach. All right, so I left it on huge print, not what I want. Integral 1/2 r squared d theta, going from a to b, alpha to beta, but we'll say a to b. All right, they gave us bounds. That's good, because I need bounds for my definite integral. So I'm looking at, on the interval of 0 to 2 pi, 1/2 3 squared d theta. And again, this is area. Just thinking about something. Anyway, so now we can clean it up. That's going to be 9/2 d theta. As integrals go, this is not a terrible one, right? Because we're anti-differentiating with respect to theta, and it's constant. So I'm just going to introduce a theta. All right, so I know if I plug in a 0, I got to plug into 2 pi first, then the 0, but I know if I plug into 0, it's going to give me nothing useful. So 9/2 times 2 pi would give us 9 pi. Nine halves times 2 pi gives us 9 pi. So if I tell you, again, that this is a circle with a radius of 3, and the formula for the area of a circle is pi r squared, you should have been expecting 9 pi to begin with. Now, it begs the question, well, would I have to do all this stuff to get credit? Well, I would be, from a student standpoint, I'd be looking forward to a question like this on a test. I would want this one. Yeah, I'd be happy to do all this work to get that answer. I know I could get it with pi r squared. I would want this question for two reasons. One, because it keeps me from having to do a harder question on this topic. All right, all skills are there. You know you have to take an antiderivative, use a formula, and so on. All right, the other thing is you already know what the answer is supposed to be going into it. All right, if I give you something that's completely unfamiliar, like a Lima song, hopefully I got that right, you have no sense going into the problem what the area is supposed to be. I don't know that I want to do arc length yet with this because let's do the area for the second one first, and then we'll get into the arc lengths all in one shot. All right, we'll go that way. Just because I think it's going to ruin my flow here.
Did you just use the calculator and just divide by 5?
Yeah, to get the yeah. So if you were like Math 9.
Yeah.
Yeah, totally. Yeah, my standing rule for those of you who are unfamiliar with my way of doing things is if it's a definite integral, you don't have to show me anything except for the answer. So depending on the instructions, you may have to have it in terms of pi, so you might have to wiggle around that. But I don't need you to actually show me the anti-differentiation technique. All right, there's going to be enough opportunities for me to assess you on your ability to take derivatives and antiderivatives in this course. So you're not going to have to worry about, like, if you have something like this, just pop it in your calculator. It's going to spit out like 29 point whatever. You know it's a multiple of pi, so divide out the pi, and like we talked about last class. So good point. And most of the time it's going to call for a decimal answer anyway, so you'd be all right. Now, for number 2, recommendation for this question, take a quick peek on the calculator and see what's going on first before you even start the problem. All right, so if I were to graph this, and again, it's just a quick peek. I'm popping in 2 plus 4 times the cosine of theta. Quick zoom 6. All right, just to get it going. Adjust your domain. So theta min, theta max should correspond with what the problem says. It says 0 to 2 pi. That's what I want. All right. So then, all right, we got that. What I need you to do, though, is make sure that this is not going to loop around more than once. All right, because what will happen is it'll go around one time, and then it might start tracing over it again a second time. All right, if that's the case, when you go to use your area formula, it might give you an overestimate of what the area is. It might give you double the area, right? It could be terrible, right? So how do you make sure that you're going far enough? Well, there's a couple of ways. One way to be, like, I don't know, is like cavalier about it, would be to put it on bold and just have a keen hawk eye, like stare at it intently. Okay, I don't think it went around more than once. The other way to do it, 2 plus 4 cosine, which is a little bit better, a lot of bit better. Take your theta max, which you know is supposed to be 2 pi, and dial it back a smidge. All right. If you dial it back a smidge, then your graph should be a smidge short of being completed. All right. It should leave a tiny little smidge of a gap. So instead of 6.28, I might put 6.2 and hit graph. Leaves it slightly incomplete, all right, telling me that 2 pi was an appropriate endpoint for this, that I needed to go to 2 pi in order to close the loop, all right? Because if let's say the domain, and this is the basis of any kind of trick question I could give you. And most of my trick questions happen based on typos that I chose to just leave and keep them as trick questions. Like for a problem like this on a test, it might be this exact question, but maybe 0 to 5 pi over 2. So 2.5 pi. So you're going overboard by half a turn, I guess. Well, a quarter a turn, right? So let's say I put 3 pi in here. It's hard to see that the motor is still running, that it's still going afterwards. But if I were to dial it back, let's say I had 3 pi given, I'll dial it back to like 9. It's still a complete graph. Dial it back to 8. Still a complete graph, which means that my domain is too expansive. All right. Now, this is the difference between arc length and area, because in arc length you might want to have a distance that overlaps another distance. Like you go around the curve more than once. Hell, that happens all the time. You run around the track. You run around the track once. You run around it 10 times. Right? So imagine this. You run around the track for like an hour straight, and somebody tells you, oh, okay, you just ran for 100 meters. You're like, no, I ran for more than that. Or like, no, I only saw you run for 100 meters. I measured the distance around, is it 100 meters around one full, or is it 400 meters? It's 400. Okay, so you only ran 400 meters. Why? Because, well, whatever the distance is around, right? Quarter mile, if we're being American about this, I guess. Because it's four laps for 1 mile, if I'm not mistaken. So they say you only ran for a quarter of a mile. And that's because all they did was they measured the length around 1 lap. They didn't account for the fact that you went around like 20 times, right? So in the case of area, I only need the distance around 1 time. But in terms of arc length, I may need it more than 1 time, less than 1 full loop. It's all sorts of possibilities. So even if I went down to 7, I'm still completing the loop and then some. It wouldn't be until I got down to 6 where I would say, oh, okay, now I'm short. So it's somewhere between 6 and 7 that closes the loop, in which case you'd settle in on pi. All right, so that's an important recognition, because if you don't know that your domain is appropriate, then it's a non-starter, right? Like you could run these calculations, but you're not going to get anything meaningful from it. All right, so in this case, we know 2 pi is good, but the cautionary tale is important. So 0 to 2 pi, 1/2 r squared, whatever your r is. This is my r. 2 plus 4 cosine theta. D theta. So in the previous question, it was a nice luxury that you were able to use your calculator. It's like, I could have done it either way, but if I want to be fancy, I guess I could use my calculator. Here, you want to use your calculator, because the only way you're getting this antiderivative is to simplify first. So distribute it out, combine any like terms, multiply through with the 1/2, and then do a trig substitution. A trig identity substitution. All right, that can sometimes be harder than just an ordinary trig substitution, because that requires you to know trig identities, like the cosine double angle identities. Right? Because if you're going to take the antiderivative of a cosine squared, you have to know that you can swap that out for a 1 plus cosine 2 theta over 2. How many people remember that from Calc 2? A couple people, right? There's always a few people, right? But the rest of us, like, oh, yeah, I guess I got to review that. Or you pop it in your calculator. All right. This is, I don't know if this is going to work. But Math 9, 0 to 2 pi. Make sure you're in the right mode, for crying out loud. That's what you should be saying to yourself during a test. Just make sure you're in the right mode, for crying out loud. I mean, you could throw some colorful metaphors in there if you want. I don't think I've ever made a mistake without cursing at myself at some point. 2 plus 4 times the cosinus of theta and then pop in your theta. If you're in polar mode, that's what comes up when you hit X. All right. If you're in polar mode, when you hit X, the theta is going to come up and you're going to be in good shape. All right, so just go back, double check that you didn't type in anything incorrectly. And again, you know, like, people either love this or hate it, but I know some of you are only in this class because I allow stuff like this, and that's fine, because we're going to do some hard math in this class. Don't worry, it'll get harder, but this is not, I mean, this is Calc 2 content. You've already been assessed on it. You got a grade for that course. I don't need to grade you again. All right? So type in your expression. Be careful about it. Make sure you type it in correctly. And hit enter. 37.7-ish. If you want, divide out a pi to see if it can clean up. It does. So this gives us a 12 pi. A very satisfying 12 pi, I might add. I keep hitting the right button expecting, I'm sorry, I keep hitting the wrong button expecting the right thing to happen. Hey, what's that all about? That's not at all what appears on my screen. There it is. Just need a little memory jog there. All right. Yeah, so we'll just focus on areas for now, because again, we're in a groove for that. So the last one I wanted to do today is the area between two graphs. So you have two graphs or two equations, which means that you have kind of a sticky situation when it comes to domains, because sometimes a domain that works for one doesn't work for another. So it may be perfect for the r equals 3. In fact, it is, because we know it is. We did it already. But it may be an overestimate for the r equals the square root of 9 cosine 2 theta. All right, so just give it a quick look in your calculator. So I'll just type it in, and then I'll show you on the big screen real quick. So the big drawback when it comes to the calculator is stuff like this. This is desperately trying to graph a lemniscate, a propeller-looking graph. So this should be connected.
No, it shouldn't.
Yes, it should.
No, it's undefined at pi over 2, 3 pi over 2.
1 second. Get back to this. R can be positive or negative and still get you where you need to go, because you're allowed to aim your R in any particular angular direction. So just because we can dismiss a particular negative R doesn't mean that it's eliminated completely, because we could always cover it with a positive R. All right. So it should be connected on the graph. It fails to do it. And that's a drawback to the graphical technique. It's kind of annoying, but we learn to live with it. The issue when it comes to something like this in dealing with the technique that we're working on is really more pronounced than that, because the method I just showed you, the idea of dialing back your domain until it shows that it's less than a completed graph, that's troublesome, because if the graph doesn't depict it as a completed continuous graph, or the calculator doesn't depict it as a completed continuous graph, then to begin with, then no matter what we do to the domain, it's not going to fix that. All right, there is something that you could do to the theta step. You make your theta step like minuscule, and it'll come closer to completing the curve, but it'll never actually look perfect. All right, so what do we do? What we can do here is actually solve and make a determination of where the loop would be closed. All right, because a lemniscate opens and closes at the pole. So what I would do here is take my r equals the square root of 9 cosine 2 theta, set it equal to 0, senior moment. So the graph is going like this, then going through the pole, then back. And so this is the key point, which is 3 units away. All right, so that's the missing unit. That was so weird. So what we're supposed to do, using a technique I like to call the right way, is set your equation equal to 3, because that's where it's supposed to close. And that should, in theory, make a lot more sense. All right, then solve. 9 equals 9 cosine 2 theta. Still need to know some unit circle trig, or at least be able to finagle a solution to unit circle trig without knowing unit circle trig. All right, but it's the same idea. So I need the values in the circle where cosine is equal to 1. All right, so
that's 0 degrees and pi.
0, well, pi would give us, 2 pi is what we want, because pi would give us a -1. 3 pi,
So 4 pi.
4 pi, any even multiple of pi, etc.
4, 6.
Don't really want constants.
Right, that's what I'm getting at. So I'm listing them all out, and then solve. 0, pi, 2 pi,